Welcome, curious minds, to the deep dive.
Great to be here.
You know, in organic chemistry, we often get comfortable with molecules behaving, well, one way.
Right, predictably.
Exactly. Alkanes are nucleophiles, aromatic rings, love electrophiles,
Mm.
standard stuff.
Mm-hmm.
But what if I told you they can completely flip their personality?
Ah, the exceptions to the rule. Or maybe the other rule.
Right. What happens when a molecule that's usually electron-rich suddenly decides to act like an electron-hungry magnet?
It's these surprising inversions of reactivity that aren't just fascinating academically, but they often hold the key to building incredibly complex molecules.
Yeah, they really challenge your intuition about how electrons flow, don't they?
Absolutely.
So today we're diving deep into that fascinating twist where alkenes and even aromatic rings, those typically electron-rich species, become electron-poor.
Inviting attack from nucleophiles.
Exactly. Our mission, drawing directly from Chapter 22 of the renowned Organic Chemistry's second edition by Clayden, Greeves, and Warren, is to truly understand conjugate addition and nucleophilic aromatic substitution.
It's a big chapter packed with really core concepts.
For sure. Think of this as your shortcut, maybe, to grasping these crucial concepts without getting totally bogged down.
We'll try to unpack the intricate mechanistic reasoning, trace some surprising reaction pathways.
You see how functional groups undergo these radical transformations?
Yeah, and touch on stereochemistry, and even glimpse how these reactions are used in retrosynthetic analysis, that art of working backward from a target molecule.
Get ready for some genuine aha moments, because we're going to clarify how even subtle changes like, temperature, catalyst, or just the molecule structure can completely alter a reaction's fate.
And this isn't just theory, it's really the foundation for designing important compounds, even life-saving ones.
Okay, so let's kick things off with conjugate addition. This is the first way alkenes sort of transform into electrophiles. Cast your mind back to early nucleophilic additions to carbonyl groups. You add a Grignard reagent or maybe cyanide to a carbonyl, especially at low temperatures.
Yeah.
And you expect a straightforward attack directly on that carbon-oxygen double bond, right?
That's the standard picture. You get an alcohol or a cyanohydrin, the CO bond is gone.
The CC bond, if it's even there, just sits and watches.
Exactly, it's a spectator.
But here's where it gets, well, really interesting. What if you just tweak those conditions slightly?
Ah, the subtle changes.
Imagine running that Grignard reaction, but now you add a tiny bit of copper salt-like, 1% UCl.
Okay.
Or with cyanide, instead of keeping it cold, you crank up the heat to maybe 80 degrees Celsius.
Right. Much hotter.
Suddenly, you get a completely different product.
Yeah.
The carbonyl group, it stays.
It's still there.
But the carbon double bond disappears. It's like the molecule chose a different kind of secret door to react through.
And this secret door is what we call conjugate addition, or sometimes 1,4 addition or Michael addition, lots of names for it.
Right.
It's a nucleophilic attack specifically on a carbon-carbon double bond, but only when that double bond is next to an electron withdrawing group, like a carbonyl.
So it's not just any double bond.
No, absolutely not. And what's fascinating is that while alkenes usually react with electrophiles, these conjugated alkenes become versatile. They still react with electrophiles.
Okay.
But now, crucially, they also react with nucleophiles. They play both sides.
Okay, let's unpack the why then. Why does this happen? You said it's about conjugation and polarization.
Exactly. We're talking about unsaturated carbonyl compounds, things like enones, enols.
Right, where alpha is next to the carbonyl, beta is the next carbon in the double bond.
Precisely. And the crucial role of conjugation is that it brings those two electron systems, the CC and the CO, into direct electronic communication. They talk to each other.
Which stabilizes the molecule overall.
It does, but more importantly for this reaction, it creates an electron deficiency, a partial positive charge at that beta carbon. Well, the electrons in the CK bond get pulled, sort of siphoned off towards the very electron-hungry oxygen of the carbonyl group.
Okay, so the oxygen's greediness extends down the chain.
You could put it that way. It makes that beta carbon electron poor and, well, ripe for nucleophilic attack.
And we can actually see this effect, right, like in the lab.
Oh, yeah. Spectroscopy gives us clear evidence. Using infrared IR spectroscopy, we see the CO and CKC double bond peaks shift to lower frequencies.
The bonds are weaker.
Exactly. Both pi bonds are weakened by this electron sharing or pulling, and interestingly, the CVC absorption often gets more intense, suggesting a larger dipole moment across that bond, more polarized.
And what about NMR?
Carbon-13 NMR is even more direct. The beta-carbon signal shifts significantly downfield.
Downfield means less electron density.
You got it. It unmistakably shows it has lost electron density compared to a normal unconjugated alkene. It's basically a hotspot for incoming electrons.
So if we're digging even deeper into the why, what's really happening at the molecular orbital level? Why is the beta carbon the target?
Right, okay. It boils down to molecular orbital control. The actual bond-forming step, the real handshake, involves electrons moving from the nucleophiles HOMO.
Highest occupied molecular orbital, where its available electrons are.
Exactly. To the electrophiles LIMO.
Lowest unoccupied molecular orbital, where it can accept electrons.
Perfect. And what's key for these unlevel unsaturated systems, like acrolein compared to a simple aldehyde, is how that LOMO is shaped. The oxygen distorts the orbitals.
Okay.
And the crucial insight is that the LMO has its largest coefficient, its biggest lobe, if you like, right on that beta carbon.
So the orbital shape itself guides the nucleophile there. It's not just about overall charge.
Precisely. It's where the electrophile is softest or most receptive orbitally.
Fascinating. So, okay, the nucleophile attacks the beta carbon. What happens next? What's the intermediate?
Good question. It generates an enolate intermediate or an enola under acidic conditions.
The enolate again. We see those everywhere.
They're fundamental. So under alkaline conditions, say an alkoxide attacks the CC, forms that enolate. Then the enolate just grabs a proton from the solvent, maybe water.
Regenerating the carbonyl.
Yep, and regenerating the catalytic base. The cycle continues.
And under acid.
Under acidic conditions, you first protonate the carbonyl oxygen. This makes the whole system even more electrophilic.
Ramps up the electron pull.
Exactly. Then a nucleophile, maybe chloride, attacks the beta carbon. This gives an enol intermediate,
which then tautomerizes
to the more stable keto product. Same overall result, different intermediate steps.
Okay, this brings us, I think, to the absolute core question here. Why does a nucleophile sometimes hit the carbonyl directly, the 12-2 addition?
Yeah.
And sometimes it goes for that CC double bond, the 1s4 addition, the conjugate addition. What's controlling this? It seems like a choice.
It is like a choice, and this is where the real puzzle begins. It's a dance between a few key factors.
Okay, factor one.
First, reaction conditions.
Yeah.
Big one. Often boils down to kinetic versus thermodynamic control.
Right, the classic speed versus stability trade-off.
Exactly. Take our cyanide example again. Low temperature, 510 degrees C, you get the cyanohydrin via direct addition. That's the kinetic product. Forms faster, probably because the carbonyl carbon has a greater partial positive charge, stronger initial attraction, but it's often reversible.
Okay, but then you crank up the heat.
Right, 80 degrees C, and you favor the conjugate addition product. That's the thermodynamic product.
Stable.
Much more stable, because think about it. You retain the strong CO pi bond and only break the weaker C pi bond. Direct addition breaks the strong CO pi bond.
Ah, okay. So low temp, short time favors the faster product. High temp, longer time lets it equilibrate to the most stable product.
You've nailed it. Kinetic control versus thermodynamic control.
Right, factor two.
The nature of the unsaturated compound itself, structural factors.
More reactive CO groups think aldehydes, maybe acyl chlorides, they tend to favor direct addition. They're just so inherently reactive at the carbonyl carbon.
Okay.
Less reactive CO groups, like in amides or esters, they're less tempting for a direct hit, so they lean more towards conjugate addition. The beta carbon gets more of a look in.
Got an example?
Sure. Butyllithium, a strong, hard nucleophile, often adds directly to an unsaturated aldehyde, but it might add conjugately to a less reactive unsaturated amide. Same nucleophile, different substrate reactivity.
Makes sense. Okay, factor three.
The nature of the nucleophile. Hard versus soft.
Ah, yes, the HSAB principle callback. Hard and soft acids and bases.
Exactly. We need to revisit that. Hard nucleophiles, small, electronegative, high charge density, like hydroxide or organolithium.
And they like hard electrophilic sites.
Right. And the carbonyl carbon is considered harder, more charge concentrated.
Okay. And soft nucleophiles.
Soft nucleophiles are larger, their electron clouds are more diffuse, maybe less electronegative atoms like sulfur or phosphorus. Think thiols are RSO, or phosphines.
And they prefer?
They prefer soft electrophilic sites. And the beta carbon of the anon, the site with the largest Lumabo coefficient, is considered softer. Orbital interactions become more important than just charge.
So thiols would be great for conjugate addition.
Excellent. Thiophenol, for instance, adds beautifully via conjugate addition.
And this hard-soft thing has real-world echoes. You mentioned termites.
Yeah, it's fascinating. Soldier termites use an anun in their defensive spray. It undergoes conjugate addition with essential thiol groups in enzymes of predators, basically poisoning them.
Wow. But the worker termites?
The worker termites have an enzyme that specifically reduces that CC double bond, making it harmless before it can react. They detoxify their own weapon. It's kind of like nature's chemical warfare and countermeasures.
Incredible. And anti-cancer drugs, too.
Yes, drugs like helena and vernolapin are thought to work, at least in part, by irreversible conjugate addition to thiol groups in critical enzymes, like DNA polymerase, stopping cancer cell replication.
So this fundamental reaction type is literally life and death.
In many biological contexts, absolutely.
Okay, one more factor, and this one seemed almost like cheating. The role of copper I salts.
Ah, the catalytic magic, yes. Grignard reagents, as we said, are typically hard. They like direct addition.
Right.
But you add just a tiny amount, like 1% of a simple copper eye salt like QC. And suddenly, that Grignard reagent switches almost completely to conjugate addition. It's dramatic.
How on earth does 1% copper do that?
It's all about transmetallation. The Grignard reagent, RMGX, reacts with the copper salt. The copper essentially swaps places with the magnesium.
Forming an organocopper reagent.
Exactly. Something like RQs. And organocopper reagents are much softer than Grignards.
Ah, so the copper makes the nucleophile soft, directing it to the soft beta carbon.
Precisely. The organocopper does the conjugate addition, and then the copper gets regenerated, ready to react with another Grignard molecule. It's catalytic.
Clever. Are there other copper reagents?
Yes, things like lithium cuprates, artiloi, often called Gilman reagents, are very well established for doing clean conjugate additions. Sometimes you even trap the intermediate enolate with something like trimethylsilly chloride before workup.
Okay, so it's not just carbonyls activating these alkenes, right?
Yeah.
Other groups can do it too.
Definitely. Any strong electron withdrawing group can play the role. Nitriles are a good example. Think acrylonitrile.
Yeah.
Amines readily add to acrylonitrile. It's a reaction called cyanoethylation.
Nitro groups.
Nitro groups are really good activators, extremely electron withdrawing. So nitroalkenes are very reliable Michael acceptors, as we call them.
Reliable meaning they strongly favor conjugate addition.
Yes. Even sodium borohydride, which usually reduces carbonyls, will add conjugately to reduce the CC bond of a nitrylcopene, leaving the nitro group untouched. Shows how activated that double bond is.
Now, building on this, what if you have a leaving group at that beta position already?
Ah, good point. Just like direct addition to a carbonyl becomes substitution if there's a leaving group.
Like in an acyl chloride.
Exactly. Conjugate addition can become conjugate substitution if there's a leaving group at the beta carbon.
How does that work?
It's an addition-elimination mechanism. Very similar, actually, to what we'll see in nucleophilic aromatic substitution soon.
Okay.
The nucleophile adds to the beta carbon, forming that tetrahedral intermediate, well, not tetrahedral here, but forming the intermediate.
The enolate, sort of.
Right, the negative charge intermediate. And then, instead of picking up a proton, the leaving group just leaves, kicked out.
Got it. Addition, then elimination. Example.
Think of methanol reacting with a beta-chloroanon. Methoxide adds, pushes electrons up, they come back down, chloride leaves. You've swapped CAL for OA.
And he said this is used in drug synthesis.
Absolutely. The synthesis of anti-ulcer drugs like cimetidine and ranitidine relies heavily on sequential conjugate substitutions. They use acarine nucleophiles reacting with things like cyanoamines or nitro compounds that have leaving groups suitably positioned. It's a really powerful way to build up complexity.
Wow, okay.
Yeah.
One last type of conjugate reaction. Nucleophilic epoxidation.
Right. This uses the hydroperoxide anion, IOU, as the nucleophile.
Which has a built-in leaving group, the hydroxide.
Exactly. And hydroperoxide is interesting. It's a better and softer nucleophile than hydroxide, HIOO, even though it's less basic.
Why is that?
It's called the alpha effect. Having that extra lone pair on the adjacent oxygen atom somehow enhances its nucleophilicity, makes it attack better.
So, mechanism.
It's conjugate addition of HOO to the beta carbon, followed by an intramolecular attack of the resulting enolate oxygen onto the adjacent oxygen, kicking out hydroxide OO to form the epoxide ring.
Okay, addition then internal displacement. How is this different from normal epoxidation like with MCPBA?
Key difference is stereochemistry. Electrophilic epoxidation with something like MCPBA is stereospecific. A cis alkene gives a cis epoxide Trans gives trans.
Because it's a concerted one-step process.
Right. But nucleophilic epoxidation is 2 steps. There's an intermediate where the CC bond, formerly the double bond, can rotate freely.
Ah, so you lose the original stereochemistry.
You often do. And because rotation can happen, it usually ends up forming the more stable trans epoxide, regardless of whether you started with a cis or transalkene.
Interesting distinction. Okay, phew, that's a lot on conjugate addition. Ready to switch gears?
Let's do it. Part 2. Nucleophilic aromatic substitution.
Right, where those famously electron-rich aromatic rings, the ones that usually love electrophiles,
Yeah, the ones we spent a whole deep dive talking about reacting with EO.
suddenly become electron efficient enough to react with nucleophiles.
This feels really counterintuitive. It does, initially. Because we know aromatic rings are stable, electron-rich. The big question is, why don't nucleophilic substitutions usually happen on aromatic halides? Like, why can't you just boil bromobenzene with sodium hydroxide and get phenol easily?
Good question. Why not?
Well, think about the standard mechanisms. SN2 at an sp2 carbon, impossible.
Why impassable?
SN2 requires backside attack, 180 degrees from the leaving group. For an aromatic halide, the CX bond is in the plane of the ring. Backside attack would mean the nucleophile coming from inside the ring.
Which is physically blocked.
Yeah.
Absurd, as the textbook says.
Exactly. And SN1 is also highly unfavorable.
Because?
It would mean the halide just leaving on its own, forming an arylocation. That positive charge would be in an sp2 orbital sticking out from the ring, not delocalized within the pi system like a normal carbocation. It's very high energy, very unstable.
Okay, so SN1 and SN2 are basically out for simple aromatic halides. So how do these substitutions happen when they do? What's the workaround?
The breakthrough mechanism is the addition-elimination mechanism, often called SNAR.
SNAR. Aromatic nucleophilic substitution via addition-elimination.
You got it. And it actually draws a strong parallel to that conjugate substitution we just talked about.
How so?
Remember the cyclic beta-fluoroenone example for conjugate substitution?
Yeah.
Addition, then elimination?
Yeah.
Now, mentally add 2 more double bonds into that 6-membered ring to make it aromatic. That conjugate substitution pathway essentially becomes nucleophilic aromatic substitution.
Whoa, okay, so the mechanism is...
The nucleophile adds to the aromatic ring, breaking aromaticity temporarily. This forms an anionic intermediate.
often called a Meisenheimer complex.
Right, a resonance-stabilized anion. Crucially, the negative charge must be delocalized into an activating group. Then, in the second step, the leaving group is eliminated, and aromaticity is restored.
Addition, then elimination. Got it. But you need specific things for this to work.
Absolutely. Key requirements.
Yeah.
First, a good nucleophile, usually oxygen, nitrogen, sulfur, sometimes cyanide.
Second, a leaving group, typically a halide.
And third, critically, an activating group. This has to be a strong electron-withdrawing group, like a nitro group, carbonyl, sulfone, or cyanide.
And its position matters, right?
Hugely important. It must be positioned ortho or para to the leaving group.
Why not meta?
Because if you draw the resonance structures for that Meisenheimer complex, the negative charge only develops on the carbons ortho and para to where the nucleophile attacked and where the leaving group is. A meta group simply can't participate in stabilizing that negative charge through resonance.
Okay, so the activating group needs to be in the right place to receive that negative charge. Makes sense.
Which is why a common synthetic sequence is nitration first, electrophilic substitution directs toward the para, followed by nucleophilic substitution, SNR.
Clever. Is there evidence for this Meisenheimer intermediate?
Yes, they can sometimes be isolated or observed spectroscopically. Often they give rise to deep colors, like purple. And NMR studies on related anions confirm that charge delocalization to the ortho and para positions.
Now, here's the bit you flagged earlier that really messes with intuition. Fluoride.
Ah, yes, the fluoride paradox.
You're saying fluoride is an excellent leaving group in SNR. Like, much better than chloride, bromide, or iodide.
Yes, often 100 to 1,000 times faster. This ought to surprise you and everyone listening.
It absolutely does. Fluoride is normally the worst halide-leaving group in SN1, SN2 because the CF bond is so strong.
Exactly. But remember the mechanism. Addition, elimination. Which step is rate determining?
Ah, the first step, the addition. Breaking aromaticity must be tough.
Precisely. The addition of the nucleophile to form the Meisenheimer complex is the slow, rate-limiting step. And what does fluoride do really well?
It's super electronegative, pulls electrons like crazy.
Right, so fluoride's powerful inductive effect strongly stabilizes the developing negative charge in that anionic intermediate. It helps the ring accept the nucleophile's electrons in that difficult first step.
So its electronegativity helps the slow step, even though it's bad at leaving in the fast step.
You've got it. Its actual leaving group ability in the second, fast step is irrelevant to the overall rate.
Okay.
It's all about stabilizing that high-energy intermediate.
Mind blown. Okay, so activating groups. Are some better than others?
Definitely. Nitro is generally the best activator, followed by groups like sulfone, nitrile, and ketone. Even a trifluoromethyl group, CFUO, can work purely through its strong inductive effect.
And this SNR chemistry is synthetically useful.
Hugely useful. Think about building complex molecules. The synthesis of the antibiotic ofloxacin is a great example.
How so?
It uses multiple SNR reactions along with conjugate substitutions in sequence to construct different parts of that quite complicated structure. It really showcases how these fundamental mechanisms are workhorses in medicinal chemistry.
Okay, so SNR is one way, but you mentioned SN1 earlier, saying it was unfavorable. But is there any way to do an SN1 type reaction on an aromatic ring?
There is one major exception: diazonium compounds. This involves the ultimate leaving group,
Which is?
nitrogen gas, N.
Anio. Very stable. Happy to leave.
Extremely happy to leave. So aryl diazonium salts, AR-N, can lose anuro relatively easily, especially upon gentle warming, to form that highly reactive aryl ligation we mentioned earlier.
The unstable one.
Yes, but because N-auro is such a fantastic leaving group, its formation becomes feasible. Once formed, this aryl cation is immediately captured by almost any nucleophile present.
So it is reminiscent of SN1, leaving group leaves first, then nucleophile attacks.
Exactly. We hope you find it reminiscent.
How do you make these diazonium salts?
Through diazotization. You react a primary aromatic amine, RNA, with nitrous acid, HONO, which is usually generated in situ from sodium nitrite, NaAros, and a strong acid like HCl at low temperatures.
Low temperatures are key.
Crucial. Alkyl diazonium salts are incredibly unstable and just fall apart. Aryl ones are more stable thanks to some resonance, but only really hang around at 0 NAPI 5 degrees C any warmer, and they start decomposing, losing that aryl.
What are the applications? Why go to this trouble?
Oh, it's incredibly useful for replacing an amino group, which you can often introduce easily via nitration then reduction with other groups. For example, you can replace NaAros with NROs just by warming the diazonium salt in water. This makes phenols you couldn't make easily otherwise.
So nitrate, reduce to amine, diazotize, hydrolyze. 4 steps to get an OH group on the ring.
Yep, a standard sequence. The synthesis of the drug thymoxamine uses exactly this strategy to introduce one of its hydroxyl groups.
Can you introduce other things besides OH?
Sure, adding iodide, like from Ki, gives aryl iodides. Using copper I, salts, KCl, QBu, QCN allows you to introduce Cl, Br, or Cn. These are called the Sand-Meyer reactions. Very important transformations.
Okay, SNR, SN1 via diazonium. Any other weird ways to substitute on an aromatic ring?
Oh yes, we saved perhaps the weirdest for last, the benzene mechanism.
Benzene sounds odd.
It is odd. Remember we said bromobenzene doesn't react under normal conditions?
Yeah, NOH doesn't do much.
But under really vigorous conditions, like fusing it with solid NaOH at like 300 degrees C, or using an incredibly strong base like sodium amide, NaNH, and liquid ammonia at lower temperatures, it does react. Substitution happens.
But how? SNR needs activating groups, which aren't there. SN1 and SN2 are out.
Exactly. Something completely different must be going on. The first clue came from realizing these conditions involve very strong bases.
Okay, so maybe a proton gets removed.
Precisely. The strong base rips off a proton ortho next door to the halogen leaving group. That proton is slightly acidic due to the halogen's electronegativity.
Forming a carbanion next to the halogen.
Yep. And then, in the next step, that carbanion kicks out the adjacent bromide ion.
Elimination.
Elimination. This forms the highly reactive, impossible-looking benzene intermediate.
Okay, wait. Benzene. It sounds like benzene with a triple bond. How is that even possible in a 6-membered ring?
Great question. It's not a normal triple bond like in acetylene. Benzene still has its normal aromatic pi system, 1 ring of 6 electrons. Benzene has that, plus an extra very strained pi bond outside the ring.
Outside. How?
It's formed by the sideways overlap of 2 sp2 orbitals, one on each of the carbons that were involved in the elimination. These orbitals point outwards from the ring.
So it's a weak, strained, sideways pi bond.
Exactly. Very weak, very strained. Makes benzene incredibly reactive and highly electrophilic at those 2 carbons.
So elimination forms benzene. What happens next?
Then the nucleophile, like the amide ion NHRO or hydroxide, simply adds across this strange triple bond.
Ah, so it's elimination addition, not addition elimination like S and R.
You got it. The sequence is flipped. Elimination first, then addition.
What's the evidence for this bizarre intermediate? It sounds pretty hypothetical.
Oh, the evidence is quite strong now. One key piece is regioselectivity. If you start with a substituted benzene, like orthochloroanisole, and react it via benzene,
Okay.
the nucleophile adds to the benzyne intermediate. Where it adds is influenced by steric and electronic factors, but often it leads exclusively to the meta-substituted product relative to the original substituent, the O-aim group in this case.
Meta. Why is that significant?
Because you absolutely cannot make that meta product via standard electrophilic substitution, which would give orthopara, or SNR, which requires orthopara activation. It points to a completely different mechanism, one where the nucleophile can seemingly add meta. Benzene explains this.
Okay, that's compelling. Anything else?
You can actually generate benzene cleanly by heating certain precursors, like 2-diazoniobenzoate, a zwitterion. It decomposes to benzyne NO and CoCo.
And it's so reactive.
It dimerizes. Benzene reacts with itself to form a dimer, biphenylene. Further proof it exists, however fleetingly.
Can you actually see it?
Directly, it's tough. But mass spectrometry in the gas phase can detect the benzyne molecule, mass to charge 76, and its dimer, Me152, providing pretty definitive proof of its transient existence. It's a fantastic story of chemical detective work.
Wow. Elimination addition via benzyne. That's wild.
It really is one of the more unusual yet synthetically useful mechanisms in organic chemistry.
Okay, let's try and unpack all of this. We've journeyed through a truly fascinating landscape today.
Yeah.
We saw alkenes and aromatic rings, usually playing the role of electron-rich nucleophiles, completely invert their character to become powerful electrophiles.
Reacting with nucleophiles instead of electrophiles.
From subtle temperature changes dictating conjugate versus direct addition,
To the catalytic magic of copper.
to the counterintuitive leaving groupability of fluoride in SNR.
And finally, the dramatic and frankly weird formation and reaction of benzene.
It's really clear that organic reactions hold so many surprises, and our understanding is always evolving with new evidence and mechanistic insights.
And understanding these detailed mechanisms, really tracing the movement of electrons, thinking about hard versus soft interactions, the crucial placement of activating groups. It's not just like academic exercise.
Right, it's practical.
It's the fundamental blueprint for how chemists design and synthesize complex molecules. We saw examples from life-saving antibiotics to natural defense compounds. It's the toolbox for building matter.
So what does this all mean for you listening? Well, next time you encounter an alkene next to a carbonyl, or an aromatic ring with a leaving group and an activating group, remember their potential dual nature.
Don't just assume the standard reactivity. Ask yourself, could it act as an electrophile under the right conditions?
What unexpected reactivity might you uncover if you just tweaked the conditions, or used a different nucleophile, or introduced a new activating group? The possibilities driven by these mechanisms are truly endless in the world of organic synthesis.
Keep exploring those possibilities.
Thank you for being part of the Last Minute Lecture family.